Let's dive into the various units that we use in gas law equations, including pressure, volume, temperature, moles, and R as our universal gas constant. Stick around to learn about each of these units and how they're applied. Before I tell you what the units are, let's do a quick quiz and see if you can identify the volume, pressure, and temperature units in the following paragraph. Go ahead and pause the video here and see if you can identify all the volumes, pressures, and temperatures. Go! Hopefully you correctly identified the units for temperature as the 32 degrees Fahrenheit, the 40 degrees Celsius, and the 350 Kelvin. The units for pressure were 1 atm, the 2,000 decimeters cubed, and the 10,000 psi. That's pounds per square inch. And the one volume unit I had in there was the 50 milliliters of the antidote after I received my second dose of COVID vaccine. Dun dun dun! Zombie. Since you were able to pick out some of the pressure units, what is pressure in the first place? It's a force per unit of area. The pressure for gases, then, in terms of chemistry, would be the sum of the force of the impacts of the gas particles against the walls of the container. If you recall from my previous video on kinetic molecular theory, KMT, we know that the fifth assumption of KMT is that these gases, when they get hotter, the temperature is going to affect the kinetic energy. And thus, when it's hotter and the gases move faster, they're going to collide with the walls of the container more often, more frequently, therefore increasing the pressure with the more collisions that they have. Before we dive into the different units that we have for pressure, which there's quite a few of them, please check out this graphic organizer that I have linked in the description below. Print it out, feel free to use it, and fill it in as we go. We're going to start with this pressure units and fill it in here so that you can remember what 1 atmosphere is equivalent to in terms of all the other pressure units that we use in gas laws. Other than atmospheres, the first one that you should recognize for pressure is called millimeters of mercury. This is based on the height that mercury goes to according to the pressure in the air in a barometer. So 760 millimeters of mercury is the sea level atmospheric pressure. We know that this is equivalent to 1 atmosphere. So if you're following along on that graphic organizer from the description below, you would want to plug in 760 millimeters of mercury is equal to 1 atmosphere. Since it's never enough just to have one unit to express the same thing, we also call it 760 Torr. You can also put that on your graphic organizer as being equal to 1 atmosphere and equal to 760 millimeters of mercury, which is equal to 760 Torr. We know that ATM stands for standard atmosphere, and again, 1 ATM is the pressure at sea level. That's why it's equal to the 760 millimeters of mercury, because that's also based at sea level. The next unit of pressure that we have is called a Pascal, which also is coincidentally the name of the chameleon in the movie Tangled. And a Pascal is a little different here because it's measured as 1 Newton of force per square meter. And its value at sea level happens to be 101,325 PA, which stands for Pascal. On your graphic organizer, you can fill in the blank for 101,325 pascals being equal to 1 atm, which is equal to 760 millimeters of mercury and equal to 760 Torr. Since writing out 101,325 pascals is a long number, we also represent it as 101.325 kilopascals. And the final pressure unit you should be aware of is called PSI, that pounds per square inch thing, very commonly used in automotives and engineering. At sea level, the pressure in PSI is 14.69. That should be the last blank on that graphic organizer. Let's move on to the variable of temperature and its associated units. The first unit of temperature is Fahrenheit. You're probably familiar with Fahrenheit. And the standard is the 32 degrees Fahrenheit to the 212 degrees Fahrenheit in the case of water, in terms of where it freezes and where it boils. In order to label with degrees Fahrenheit, use a little circle in the kitty corner and an F to symbolize the Fahrenheit. The next unit of temperature is Celsius, and the standard for that is 0 degrees Celsius for water where it freezes to 100 degrees Celsius for water where it boils. We label degrees Celsius with, again, a little circle in the kitty corner and a C for Celsius. If you wanted to solve for degrees Fahrenheit and you had degrees Celsius, you would use the following mathematical setup. You would take the degrees Celsius, multiply it by 9 divided by 5, plus this 32 here, because that happens to be where water freezes in Fahrenheit, in order to convert for Fahrenheit. Of course, you can just rearrange this equation respectively in order to solve for Celsius if you were given Fahrenheit instead. The last type of temperature, the one that we're going to use in gas laws, is called Kelvin, symbolized by a K. This is based off of the Celsius scale, but it's set so that 0 is as small as it gets. There's no like negatives. Just like in Celsius how you can have negative degrees Celsius, in Kelvin, 0 is as cold as it gets. Ever. And since 0 is as low as it goes, there's no negative numbers. This is handy because our gas laws end up dividing by temperature. And if you're familiar with the laws of math that dictate all mathiness, you can never divide by 0. And so Kelvin is the answer for this problem. We label it with just a K, no little degree symbol, just a K. And the way you calculate it is you take degrees Celsius, not Fahrenheit. You must have it in Celsius, plus 273, and that will always get you units of Kelvin. So why is 0 the absolute minimum for Kelvin? Well, 0 is the assumed point at which all molecules stop moving or vibrating or gyrating entirely. So imagine any tiny little bond between two atoms literally stops moving. It ceases to move, vibrate entirely. By the way, that's impossible. We've never even done that. K equals 0 is literally unattainable as of this point in time, not even in outer space. So 0 is literally the point at which everything stops moving. It's so cold that it can't even vibrate. So to help you understand this concept of where Kelvin falls on the scale between Fahrenheit and Celsius, well, for Fahrenheit, 0 degrees, it's really cold outside. Remember, 32 degrees is where water freezes on the Fahrenheit scale. And 100 degrees, it's really hot outside, as those of us who live in Arizona would know, because we reach values of like 120 up here. For Celsius, it's fairly cold outside at 0 degrees Celsius. That's where water freezes. However, at 100 degrees Celsius, you're dead. What about Kelvin then? On the Kelvin scale, if you're at 0 Kelvin, you're dead. That's where all molecules literally stop vibrating at an atomic level. And at 100 Kelvin, you're also dead. Remember that degrees Celsius plus 273 is equal to Kelvin. So if we had 100 Kelvin, to figure out what the Celsius would be for that, you would subtract 273 over, and 100 minus 273 gives us a degrees Celsius of negative 173 degrees Celsius. So yes, you are dead at that temperature. Now that you've seen me sort of quasi-playing with that equation for degrees Celsius to Kelvin calculation, go ahead and try these calculations where you convert to Kelvin before I give you the answers. Ready, go! All right, so hopefully all you did was add 273 to each of the degrees Celsius values, not the degrees Fahrenheits. And you should have found the following temperatures in Kelvin for each of these locations. So check out the surface of Neptune. The surface of Neptune being negative 200 degrees Celsius, 63 Kelvin. Remember how I said you were dead at 100 Kelvin? Well, yeah, that's like the surface of Neptune. It's not that far off. Yikes. And then check out the opposite of the spectrum, the surface of the sun. Holy heck, 5,778 Kelvin. That is bloody hot. Now that we've gone over both pressure and temperature, it's important to note what this STP thing is. In the gas laws, STP stands for standard temperature and pressure. And anytime you see STP or you see a question written, something something is at STP, you are assuming that they're saying the temperature is 0 degrees Celsius, which is equivalent to 273 Kelvin. And then you're also assuming they're saying that it's 1 atmosphere. So anytime you hear standard temperature, 273 Kelvin, anytime you hear standard pressure, it's 1 atm. It's assumed that you will know those values if all that's stated is STP. If you happen to see a gas law with an N in it, that means that there's moles in that gas law. So let's give it a try. If we see PV equals nRT, that N right there is meaning that there's going to be moles in that equation. And this bottom equation, volume divided by N, those N's are representing moles. Moving on to volumes. Any amount of space that an object occupies is its volume. And the units of volume can be liters, milliliters, decimeters cubed, which is equal to 1 liter. That's really important to remember. And centimeters cubed, which is equivalent to 0.001 liters. So anytime you have a side times another side, that's 3 sides, hence the cubed, you end up with a volume. And that's also why your units end up being cubed. So if you see any cubed in the corner, you know that that must be a unit of volume. The important thing to note here is that 22.4 liters at standard temperature, which is the 0 degrees Celsius or 273 Kelvin, and standard pressure, which is your 1 atm, is going to be equivalent to 1 mole of gas. Again, in gas laws, it's assumed that you remember this conversion factor. You can use this fact to convert from volumes to moles or vice versa, because 22.4 liters of any gas at STP is equivalent to 1 mole of that gas. And as we've seen in the past with stoichiometry, you can flip this domino to fit your need for any conversion.
So what is this R variable in the gas laws? Well, first, what is a pirate's favorite letter of the alphabet? You might think it is R, but actually it is the C.
The universal gas law constant is known as R. It's symbolized as R, and this number changes depending on the units you're using. However, the two that you should be familiar with are known as 8.314 liters times kilopascals divided by Kelvin times moles. So notice that this involves the units of volume, pressure, temperature, and N for moles. Literally all of the things we just talked about for gas laws. Or 0.0821 liters times atmospheres as the pressure difference divided by Kelvin times moles. Notice that the value changed depending on the unit of pressure used. So how is it that we found out we needed to use an R universal gas constant anyways? Let's do some backwards deductive reasoning. If we know for the second R value here that we have units of liters, atmospheres, Kelvin, and moles, let's plug that in for what it would be at standard temperature and pressure. We would have 22.4 liters of a gas at standard pressure, which is 1 atm, divided by the baseline for standard temperature, which is 273 Kelvin, times 1 mole, because we know that 1 mole is equivalent to 22.4 liters at standard temperature and pressure, which is what we have signified here. So literally, if we just take 22.4 and divide it by 273, we get a value of 0.0821. And that's where this R gas constant comes from in the first place. The other thing you're going to see a lot of in gas laws is these proportionality things. We're going to symbolize proportionality by the fishy symbol. I like to call it the fishy symbol anyways. That's an equality between two ratios or values. So using this proportionality concept, we can say that something varies directly or via a direct relationship, which is signified by a straight upward line on a graph. Or we can say through this proportionality that it has an inverse relationship, which would be signified by a curved downward line on a graph. You can also have proportionality in terms of directly and inversely represented as follows. If we're talking about directly, we're implying that if one goes up, so does the other. And we can represent that as A is proportional to B. That's the little fishy symbol. And then we can take that relationship and represent it mathematically by saying K is equal to A divided by B to mean the same thing, but just in math world terms. Likewise, when we say something varies inversely, we're saying that as one goes up, the other one goes down. And we represent that as A is proportional to 1 over B. And mathematically speaking, we say that A times B then would be equal to K. So if you were working in a lab and you plotted volume on your y-axis and pressure on your x-axis, and you ended up with a curved downward data set, but then you also plotted 1 over V on your y-axis and pressure on your x-axis, and you ended up with a straight line, which of these plots would be indicative of a direct relationship? Hopefully you see that this plot would be the direct relationship because our data shows us one is proportional to the other. As one goes up, the other goes up. Whereas the inverse relationship shows this downward slope on the graph, and that is showing that as one goes up, the other goes down, or vice versa. Before you move on to the gas laws in this gas law series, make sure you test yourself on the ability to identify the pressure, volume, temperature, and moles in the word questions you'll be able to solve after learning the gas law equations. For these first 3, all I want you to do is circle any volume units, square around any pressure units, write an N over any moles that you might encounter, and underline any temperature units you see. You should also know off the top of your head what the two R values are with all of their units. That's the whole liters, atmospheres, kelvins, and mole thing. You should also know what N symbolizes and what the value is along with the units for both standard temperature and pressure. Please make sure that you're very solid in this information before moving on to calculating with gas laws. That'll make your life in the gas law world a lot easier. In this video, we discussed important units of pressure, including atmospheres, millimeters of mercury, Torr, Pascal, and pounds per square inch, PSI. We also discussed units of temperature, degrees Fahrenheit, degrees Celsius, and most importantly for gases, Kelvin. And in order to convert temperature to Kelvin, we need to take the degrees Celsius plus 273. We talked about volumes and how any cubed unit is going to signify a volume, but more frequently we use liters and milliliters in chemistry. We know that 22.4 liters is equivalent to 1 mole at standard temperature and pressure. We learned that when we look at gas law equations, that N will symbolize moles. And lastly, we found that R is the universal gas law constant, in which you need to know 2 R values by heart. Please give this video a quacks up, and please subscribe to Duckonta for some more ducky chemistry content. Quack you later.
No ducks, no glory.